Welcome to lecture 25. So we will discuss commercial real-time operating systems in this lecture. So in the last class we did discuss a few free real-time operating systems. So that did include Monta Vista, which was approach 1 what we called. So it was a patch on Linux basically. It was a new form of Linux. So that didn't survive quite a bit. We did discuss RTAI and RT Linux, which were in a combination of patches and dedicated kernel modules, which relegated the kernel pretty much to the lowest priority real-time task. So in this lecture today, we'll discuss one more free RTOS, E-cos, and then get into reviewing a few commercial RTOS. So let us look at E-cos, the embedded configurable OS. So I did try out the link. So the link is still alive. So this is intended for embedded applications, especially for systems where there is an extreme memory constraint. So all the resources that it requires in terms of memory is in tens of kbs. It's not in megabytes, it is not in gigabytes, it is in tens of kilobytes, which is quite modest. And this is something that can be developed. And many of the operating systems in this category are host target operating systems, where the host can be a Windows desktop, a Linux desktop. The entire application can be developed on the Windows or Linux desktop. There will be some sort of a virtualization layer that'll be running E-cos or simulating E-cos on the host. So this is how an application can be developed and deployed to the target. So the history of E-cos, it was initially developed by Cygnus Solutions, which was then bought by Red Hat. In early 2002 itself, Red Hat had ceased the development of E-cos, but E-cos was then transferred to the Free Software Foundation, so it still kept on developing. And at least as of 2022, as I said, the link works, and I can also see some sort of a community there which is taking care of E-cos. So how does E-cos work? Well, there is only one process. It can support multiple threads. It is configurable in the sense the OS can be easily customized to different kinds of application requirements. But the key point is that multiple processes are not supported. The APIs per se are compatible with two of the standards. So we have discussed POSIX, but then there is a Metron standard. So you can Wikipedia for this. So it is a standard like POSIX again for embedded and real-time devices. So E-cos as such is targeted for extremely high volume devices in the sense that it's a very small and reliable operating system. So it is targeted for consumer electronics, telecom hardware, automotive, right? So now smart cards are pretty much in vogue, they are in fashion. So this is where an automotive application actually makes a lot of sense, right? And so a normal smart car would have hundreds of electronic units, and you would also see the dashboard and the graphical user interface and so on. So embedded real-time operating systems make a lot of sense in this particular ecosystem. So similar to RTAI and what we have been seeing, the real-time tasks run in kernel mode. So in fact, there is no user mode. So everything is in kernel mode, which makes a lot of sense for devices of this size. It is implemented using C++. So it's a regular C++ application. So if I were to show a diagram, so if I start from the top, so mind you, there is no user and kernel over here. It's all kernel. So we have applications, we have C libraries, compatibility libraries with POSIX and Metron, compatible with both. Supports a very simple web server, a very simple networking stack and file systems. It's amazing that in this small, uh, tens of kilobytes memory, how much they were able to fit. And then, of course, there is this small kernel over here that works in conjunction with the libraries and the application, right? And so this is the target independent part, and then there is something which is specific to the driver. So, but again, it's all in the kernel. So there is a small boot ROM, a hardware abstraction layer. So as we have seen even earlier, that a lot of the uh, new features that go into a real-time operating system actually go here, where the directions of where the targets of interrupts, exceptions, and so on are changed, right? So in this case, of course, there is no reason for doing so. The reason is that we are not running a separate kernel as the lowest priority process. But still, an hardware abstraction layer is required because the hardware and the motherboard can change, may change. And then some very basic device drivers for flash drives, serial ports, and Ethernet. And then, of course, we have the target hardware, which is again very simple. So, what we can see is that all the basics are all intact. In a sense, we have a hardware abstraction layer, we have device drivers, we have the application and different subsystems of the application. So features, it does provide a choice of scheduling algorithms, timers and counters. So we are seeing these as kind of standard. Then support for interrupts and exceptions. So basically this is where we need some real-time support for masking interrupts and to have a priority regime for interrupts. Given that everything runs in the kernel, this becomes much easier. And then we need support to connect with the host, particularly for debugging. So once an application is deployed on the target, it is very hard to debug it. But then, of course, if there is a dedicated port that is sending debug information, we can do the debugging on the host. So this is needed. So if I were to compare between E-cos and RT Linux, a thread creation latency in nanoseconds, or let me maybe quote my numbers in microseconds. In RT Linux, it's 137 microseconds. Here it is much, much smaller. So, right, it is 16 to 34 microseconds. Similarly, thread deletion latency is 5 to 6 microseconds, slightly more in RT Linux. Mutex latency, this is very important. So this is between 5 and 25, whereas the equivalent number is 5 and 46. So in that case, given the size of RT Linux, it actually doesn't perform that bad. The main difference arises in the thread creation latency, most likely because RT Linux does much more of bookkeeping. So if I were to do a comparison, let us do it on this basis F, P, and N, where F is full support, P is partial support, and no support. So coming to real-time threads API, so all three of them, RTAI, RT Linux, and E-cos have a lot of support. E-cos has slightly lower amount of support, lesser support. Real-time messaging, quite similar. Multiple scheduler policies. So RTAI and RT Linux have, of course, full support for multiple scheduler policies, but E-cos in that case is slightly lacking in the sense it's partial. And that's also, you need to understand that the first two are addenda to a regular Linux system, but E-cos by definition is a very, very small system. Nobody supports distributed clock synchronization, not required. Communication with non-real-time processes. So we have seen the mechanism that uses these shared memory queues, FIFO queues, in RTAI. So that is doable. And so in E-cos actually it doesn't make a lot of sense because everything is still in kernel mode, and in RT Linux it is partially supported. libc API, well, all of them support, but again RT Linux doesn't support to that extent. C++ standard library, so this is so E-cos is still a C phenomenon. It's written in C. It's not in C++, so that is why it doesn't support, right? And the same holds also with real-time networking, where these don't appear over here. All three of them provide flexible access to interrupts, right? And so that there is full support, and they are documented to different extents. But E-cos does have a very good documentation, and I also did verify that, in the sense you can go to the site and you will see fantastic documentation on the site. Now let us discuss the MicroC OS 2. So this stands for the Microcontroller Operating System version 2. It's a very small real-time kernel. the memory footprint is about 20 kilobytes for a fully functional kernel, something quite similar to E-cos. And the source code is also, not much. It is 5,500 lines, mostly in, pure C, pure ANSI C. It is open source, so it follows the pattern and trend of many other operating systems which are open source, but they are not free for commercial usage in the sense that if you want to commercially use it, then you need to pay a fee, some sort of a license fee or a royalty fee to the maker of the software. So it was maintained by Micrium Inc. and it can be licensed for a single product or for a product line. For a product line is for a bunch of products. So it was designed similar to E-cos to have a, well, I shouldn't be calling it E-cos, it is ECOS, a small footprint. It can be used in very small 8-bit embedded platforms and upwards, of course. It is a preemptive real-time multitasking kernel. And again, memory management does not use pure virtual memory, but it uses fixed size partitions where these partitions are allocated to tasks. So this is a reasonably popular operating system in the sense over 100 microprocessors are supported as of today. So this muCOS 2 has a very rich feature set. So it is amazing that with such few lines of code, how much of functionality is packed into it. So it has a bare bones file system, runtime monitoring, again a networking protocol. It's quite amazing how much of technology is packed in. Plus, many of these things also come with add-ons, so they don't really come within the 5,500 line budget. We need to get additional add-ons and install them on top of the basic muCOS 2 kernel. But nonetheless, this is what the entire system can be made to support: networking, HTTP, graphical user interfaces, USB devices, the controller area network, which is mainly for automotives. So they use the controller area network in their system and a flash loader. They have a small footprint, and this OS is quite scalable in the sense it can also scale to a large number of devices all working together. So the schematic is that we have an application, we have a CPU independent part, where as you can see the core kernel is provided, message boxes are provided, memory features, mutex features, semaphore, task and time. So that is like the core of the OS, which is CPU independent. And then we have parts of the code that are specialized for a given CPU, like it's like a CPU driver. Along with that, we have a motherboard driver, which is known as the board support package. So that is for the target board. So because that given CPU can be hosted on different kinds of motherboards, hence there is a need for both a CPU driver as well as a motherboard driver. And the motherboard driver in this case is known as the board support package. So as you can see, we don't have a lot of files, but whatever we have is enough to run a fully featured operating system. So I would request all the viewers of this video to kindly take a look at what exactly does muCOS provide and try to understand the code. So again, let's look at specific features of this. So this is a real-time OS. It can manage 255 tasks. It supports the complete TCP/IP protocol stacks. But again, as I said, many of these things come as add-on modules. So IP, TCP, everything has a USB driver and USB core. Excellent support for vehicle communication buses such as CAN and everything related to CAN. Excellent support for other IO protocols such as the serial port protocol, RS-232, TCP/IP, USB, and JTAG. It also supports the basic shell, which can be used to talk to the OS and invoke kernel services, and also an LCD display. The file system is the regular FAT file system, which is also what USB drives and CD drives use. And it also includes a few other drivers, or let's say drivers can be written and they can be included with the basic muCOS source code. Now let's come to two more iconic real-time operating systems. The first is VRTX. So VRTX stands for Versatile Real-Time Executive. It was developed by Reddy Systems in the 80s, which was subsequently acquired by Mentor Graphics in 1995. So Mentor Graphics is a top EDA company. So they did, or they must have found a lot of value in acquiring the operating system. They were using it for system on chip architectures where we have chips that do different things, right? They're all put into one die pretty much. And traditional embedded systems. So the kernel here also was very small. As we can see, it was initially in kilobytes, 4 KB in size. So the moment a kernel is so small, naturally it will not support many of the required functionalities. So hence it could not be used as a fully featured RTOS. But then over time, multiple versions came up, and then the feature set also increased. The supported feature set also increased. So first let's look at VRTX MC. So we did talk about two variants, VRTX SA and VRTX MC. So let us first talk about VRTX MC or microcontroller. So it was optimized for low power consumption and low ROM and RAM sizes. So the kernel again occupies a few kilobytes. Those days it was intended for embedded applications such as cell phones. But we all know that in the last 20 years, which way the cell phone market went. So now cell phones basically support Android, which is a fully featured operating system, not real time. So this was the first commercial real time operating system which was certified for usage on aircrafts by the Federal Aviation Authority, which is the regulator in the United States, and for safety critical applications such as avionics. So basically here there are very stringent requirements. But the fact that many of the real-time algorithms come with guarantees definitely does help. So VRTX MC was targeted for embedded products, as I've just been describing. Here memory efficiency and low power consumption are quite important. So some of the earliest products would be set-top boxes for cable TVs, digital cameras, video game systems, internet routers, and handheld computing. So of course, internet routers nowadays use much more powerful processors, and many of them also use Linux. And these are tailored versions of Linux which give more or less soft real-time guarantees. This is all that is required. So Motorola cell phones also started with VRTX MC, but as of today, the cell phone hardware has gone so far that there is no real reason for using such small operating systems. We care more about features instead. As long as some basic real time features such as audio, video, and of course, the most important feature, which is calling, right? The phone. As long as they work, we are fine. Then came VRTX SA. So this was much more scalable. It was POSIX RT compliant and designed for larger applications, medium and large, with extensive I/O support, memory protection, reduced interrupt and task switch latency. So SA of course here stands for scalable architecture. So what are the features that it brought in? Well, it brought in support for priority inheritance and multiprocessors. So many times we have underscored the point. What exactly is the issue with multiprocessors in the sense what is our problem with spin locks and so on. Furthermore, system calls were made preemptible, which is again one of our requirements, and the time that they take was made deterministic, which is something that we need, right? So determinism increases predictability, and that is how guarantees can be provided. So an example used would be the Hubble Space Telescope, which uses the VRTX operating system. Next came VXWorks, which was developed by Wind River Systems. So Wind River Systems is again a very iconic company in the real-time sphere. So it was acquired by Intel in 2009. So VXWorks So again, this is a part of an urban legend. So these could be apocryphal stories. So I definitely don't stand by these. And again, the author of these slides may have had more information to write it down. So this is not something that I can comment on. But the story goes that in the early 80s, VRTX didn't work all that well. So Wind River extended it, and again this is apocryphal. So I would defer to the original author for the source of this. But it is believed that VXWorks stands for VRTX that works. Okay, that's fine. Not the most charitable name, but nonetheless. So VXWorks in itself is extremely iconic. So let me tell you my position. So my position is that in science, in engineering, we make products. Products definitely have some flaws. They have some shortcomings. And later products always build on earlier products and try to remedy the flaws and shortcomings. But just because a product has a flaw or a shortcoming should not count against it, because it's still, the engineers are doing the best given the time, given the market, and given the resources. So I personally hold all these operating systems, starting from what we have covered: ECOS, muCOS, VRTX, and VXWorks, all of them in very high regard. So VRTX, as we have discussed, did support a few basic features, which was the fact that, and its main problems were it lacked a functional file system, and it didn't have a very good development environment. So this is where VXWorks came in and provided a full feature set and also a development environment for a target host kind of deployment. So this was a host target kind of deployment. The kernel was still monolithic. It did support real-time POSIX standards in addition to its own API, of course. And VXWorks was used. It was indeed used in a lot of practical systems of very high value. That would include Mars missions, Honda robots, internet switches, MRI scanners, MRI machines, a big use, and car engine control systems, again very important. Key features of VXWorks. So it did support multiprocessors very well, a multitasking kernel very well, with preemptive scheduling and round robin scheduling. In terms of memory protections, instead of running everything in the kernel, as we have been seeing with Xenomai and RTAI and so on, uh, user applications, which are user real-time applications, were isolated from the kernel, which, if you would ask me, is very important because we are always concerned about malicious security breaches, inadvertent security breaches, and that is why a degree of separation is required, which VXWorks brought in. So this is a departure of our thinking from what we have been seeing, where you know pure user applications can be run as maybe the zeroth priority task, but other real-time applications are kind of sit beside the kernel and have full privileges. But this is where VXWorks differs and differs in the right direction, in my opinion. So it had a preemptive priority driven scheduler, range 0 to 255. A user can lock a task. So this is again something new. We have not seen it up till now. So locking a task basically means that regardless of the priority of other tasks, regardless of interrupts, this task will continue to run, right? It cannot be preempted. So locking a task sometimes is very useful. And of course, in the mutexes and semaphores with priority inheritance, so we have seen this earlier as well. So again, features. So it did have a shell-based user interface similar to all other real-time OSs. A file system. Again, this is what differentiated VRTX and VXWorks. It did have a full featured simulator, which again is important. Otherwise, how do you do a host target kind of deployment? That is not going to be possible. So basically, that is what that was there, and also it had capabilities for symbolic debugging. So symbolic debugging basically means that we take a look at the value of the variable, not the value of the variable, the code basically, and see what are all the statements that are using the variable and how are they doing and what properties we can maintain. So basically, based on the semantics of the code, so that would be symbolic debugging and performance monitoring tools. So this had a very rich feature set with a wide variety of tools for actual deployment, right? So as you can see, this operating system VXWorks was in itself very market focused. Other features, it did reduce the context switch time using a trick that server processors used to use at that time. So what they used to do is that they had a very large CPU register file. So they would say that maybe one process would use these registers. So this was known as a register window. The moment it context switches, so what do? We read these registers, we store them in the interrupt handler, which again stores them in the kernel stack, and then they are restored. So instead of doing that, let us just change our mapping of architectural to real registers. And instead of using this part, let me just use a few more. So essentially, you have a large register file such that every task is given its private set of registers such that there is no need to spill them to memory and restore them back. So this is known as a register window, which was there to a large extent on microsystem machines. And this was actually one of its key features, which gave it a lot of performance. So the reduced context switch time in VXWorks is pretty much because they also use register windows. But they also do something smarter in the sense they profile the register windows, and sometimes you may run out of space in the sense that you will have too many outstanding tasks. So it figures out what to keep in the register file and what to save in memory and restore later, right? So that was an important thing. And of course, if a task is not being used, you can get rid of its register context entirely. And uh, this follows from the definition of a register window that when the context of a task is restored, you only look at the correct register window. And also, along with register windows, there was a register cache which was dedicated to storing the registers, right? So basically, they went one step further and created a small memory within the CPU, which was dedicated to storing the values of spilled registers. Memory protection in early versions of VXWorks applications did run in kernel mode, the isolation was not there. But gradually, a thin virtual memory library came up known as VXVMI. And this did require hardware MMU, memory management unit support. But the latest and greatest versions of VXWorks do use some form of virtual memory. Application development was easy. You can do it on Unix or Windows based machines. You can have a cross compiler. So the cross compiler, what it would do is that, consider a regular Linux machine running on an Intel core, right? i7, i10, i9, whatever. Consider it to be i9. So the cross compiler would basically take the code and it will compile it for the target architecture. So that is known as a cross compiler. So this entire development environment, inclusive of the cross compiler, was installed on the Unix or Windows host. And it was also possible to test the entire application using VXSim before it was actually deployed. There was a Tornado IDE. An IDE is an integrated development environment which used VXWorks as a target OS with tons of application building tools. So as I said, VXWorks, is a very market focused operating system. So that is why the entire set of tools come along with it that include a cross compiler, debugger, host target communication, running debugging and monitoring tools, and a simulator, of course. What products use VXWorks? So VXWorks has seen a lot of use. So it has seen use in Mars missions, in Mars rovers, it has seen a lot of use. So several spacecraft as well, such as a deep impact mission. It's definitely seen in aircrafts, the Boeing 787 airline, the LynxOS wireless router, And it is there in tons and tons of medical solutions. For example, Siemens Medical Solutions. So Siemens is a very big vendor of medical devices, and they use VXWorks and also industrial robots. So heavy usage. So given the fact that we have seen the simple ECOS, then seen the MCOS, muCOS, and then we have seen two products which are more or less in the same genre, which is VRTX and VXWorks. Let us move to one more such proprietary product called known as Lynx. So Lynx is still alive, and it's alive and kicking in the sense it's very popular. So it was first released in 1988, long development history, fully preemptible kernel, which is very compact and reentrant. So unlike other operating systems, this does use a microkernel design. The microkernel is small. It's not very large. It's 28 kilobytes. And the aim of the microkernel is to provide essential services such as scheduling, very important, at least a bare bones version of scheduling, interrupt dispatch, and synchronization. So, as we have been seeing even in previous lectures, wherever and whenever we have a microkernel, it provides all of these features which are considered to be very primitive and very basic. So, basic scheduling, interrupt management, handling, and dispatch, and multiprocessor process synchronization. So, other services, of course, are provided as plugins, KPIs, as we have been seeing in other OSs as well. The KPIs themselves can be multi-threaded, and also they can provide, other services such as I/O file systems, TCP/IP networking, and streams and sockets in a multi-process, even a multi-machine environment. So let's now touch on the issue of microkernels. So we have seen that they take away a lot of the work from traditional kernels. They're small. They are very easy to port, maintain, and extend as long as the interface to the microkernel defines is what is kind of respected by all the KPIs or the add-on or the plugins, right? So basically, as long as the contract between the kernel and the plugin holds, using microkernels, particularly for real-time systems, is not a bad idea at all. So they are not as fast and efficient as monolithic kernels, but if you take in the advantages of flexibility, the advantages of adding and removing modules and plugins maybe at runtime, this entire thing works very well. And the microkernel itself, as we have discussed in the previous slide, mainly would provide process management services, IPC services, IPC inter-process communication services, and some memory management services. So the Lynx OS can function as a multi-purpose OS, right? Uh, Basically, along with the microkernel and plugins. The multi-threaded KPIs can do a lot. And to invoke a KPI, we do not need a context switch, right? So that is important. A context switch is not required. So when a request for service message is sent to a file system KPI, it doesn't run in a separate context that you need a context switch. So basically, this is pretty much like a function call, pretty much. The runtime overhead is low. And also, one KPI may call another KPI. So the inter KPI communication also incurs a low overhead, very few instructions. And also, the Lynx OS is self hosted in the sense that you are not necessarily restricted to a target host kind of setup, right? So, that is not a setup that is restricting you. The development of applications can be done on the same system. So, it is self hosted in that sense. The kernel is protected, and we have, similar to VXWorks, a memory management unit in both software and hardware to provide a degree of isolation between user applications and the kernel. So, what more, it supports a single scheduling policy. At least this is not something to our liking, because many other operating systems including baseline Linux, do allow you to write a user land scheduler, which can bring in many sophisticated heuristics onto the table. So it supports fixed priorities, it is preemptive with 256 priority levels. Again, this is not something which is in line with VRTX and VXWorks, which is that the clock tick frequency is fixed at 100 Hz, which means one tick is every 10 milliseconds. This does limit the resolution of timers, particularly when we have seen RTAI and Xenomai supporting nanosecond level timers. So this, in a sense, is limiting us, right? So this is not in a totally state of the art. And after we have finished Lynx, let us again come to another very popular, again proprietary real-time operating system, QNX Neutrino. So the key feature of this is that again this is heavily used. It's POSIX compliant, and of course the early efforts did start in the University of Waterloo, but then the development took up a different dimension. So the idea is that this is also microkernel based, the same way as LynxOS. There's a software bus, and pretty much all the components plug into it, like a process manager, file manager, right? Different kinds of file managers. The application for sure, right? As you can see, it's one of the components that plugs into a bus. So I'll talk a little bit about the bus-based design at the end, but let me look at the other things. Then, of course, we have the graphics manager and the network manager. So this design is not very uncommon. So many real-time systems, including the robot operating system, which is used in many robotic systems today, all of them use a software bus. So basically, this is like a publish subscribe system where you basically say that this is what I'm offering, in the sense somebody has clicked a key on a keyboard and I'm offering the value of the key. So then there could be many subscribers. Maybe the file manager may be interested, the process manager may be interested, so they will read it from here. So this is a standard design pattern. It's known as a publish subscribe design pattern. Well, publish subscribe is again not exactly this, in the sense that you subscribe for certain events, and when the publisher produces them, you automatically get a copy. It's not really a bus, but again, a bus is a generalization of all such architectures that allow many to many communication between the components. And if you think about it, of course, there is a high overhead in the sense that we are not directly calling functions. But again, the sheer flexibility and the ability to guarantee that certain properties hold, real time properties in this case, is much easier. So it has a microkernel based design where the kernel would provide the same usual thread related services, creation, deletion, communication, etc., and time related services. It's quite flexible in the sense developers can turn off any functionality that they do not require. And QNX Neutrino, so the kernel itself, so there is another fun part of this bus based design, which is quite different. So this kind of differentiates Neutrino from others, but it is pretty much in line with the robotic operating system, ROS as it is called. Now, the kernel never runs on its own. It never has work for it to actually run on its own. It's never scheduled for execution. So it is always in a response mode, that some user application or some other module or plugin needs a service from the kernel. So the kernel will execute and it will send the result back. So in a certain sense, the kernel appears to be somewhat stateless, even though it is not. But as I said, unlike regular operating systems, so the kernel will schedule itself and do bookkeeping or maintain other data structures. In this case, that doesn't happen. Only when we make an explicit kernel call or there is an exception or interrupt, then only the kernel will come up. It will get swapped in. It will do its job and then get swapped out. So the interface that we have for the neutrino microkernel is that we have, on the bus, we have events that come from threads, the scheduler, synchronization, signal, message, channel, timer, clocks, and interrupts. And the objects that we deal with, right, so whose state we change are threads, connections between threads, same machine, different machine, the scheduler and the dispatch mechanism, timers, the interrupt mechanism, the interrupt vectors, right? So basically, the key point is that the bus-based design reduces the kernel to one task, which is passive in the sense it's not active. So basically, you give it a job, it'll do it and send you the response. But otherwise, it does not have the supervisory role that it has in other operating systems. So, along with drivers, applications, protocols, and file system, so basically, what else does it provide, and also how does it provide these things? So, many of these things actually run outside the kernel in an isolated memory protected user space. One advantage again of this distributed bus based design is that any component can fail at any time. It can get restarted. This will not affect the other components. That is the way the system is architected, that we have a very loose coupling or a very weak coupling between components. Very good application portability, POSIX RT compliant. Almost every service in this case, as you can see, because there is a large amount of decoupling, every service will run as a user process. And again, we have some specialized processes over here. So one of the specialized processes is called the proc process, which performs process creation. And the microkernel does help in memory management. But it's very interesting how the microkernel itself runs in a very passive mode, where its job is to only respond to messages and events and not take a more proactive role. So you can think of it as a distributed OS where the kernel just sits somewhere, it's connected to the software bus, and its role is actually quite limited. So basically, even internally, it is distributed. And of course, you can extend the idea and make many of these components run on other machines as well. Let's now look at another important operating system called OSEK VDX. So this was an open system, right? So it's OSEK is German for open system, as you can see. I don't understand it, but this is what it means. So it was open for automotive electronics primarily because cars these days have a lot of processing units that are connected. So VDX means a vehicle distributed executive. So we will have a lot of application software, the OSEK operating system, and a microcontroller. So this is one of the very few operating systems that are explicitly dedicated for a vehicle. So it's capable of running on a ROM, and there are two types of entities, interrupts and tasks primarily. So what we see is that if we take a look at the different OSEC entities, so let's start with the highest priority, which is at the level of interrupts. So basically, we can have different kinds of interrupts, some that are bundled along with OS services, some that are not bundled. And so if interrupt processing, particularly in a vehicle, is very important. So if you think about it, in an automotive, we are not doing a lot of general purpose processing. Our main role is to basically record interactions and ensure that, let's say, if a brake is pressed or we are getting some sensor input that maybe a collision is happening, we need to deploy airbags. So all of those are what is required in the sense like QNX. We mainly have to be reactive in the sense an event happens and we react to it. So that is where we will run many of these small processes with different levels of OS involvement. The OS, of course, will be there, so it will run at a slightly lower priority than the interrupt processing. Interrupt processing has the highest priority, and then a bunch of user level tasks where different levels of preemptibility will be supported. So this ends our very comprehensive discussion on a large number of dedicated real-time embedded operating systems, both open source as well as proprietary.